Hey everybody, part 2 of parametric curves. We're going to look at a couple FRQs from 2010 and 2006. So number 3 from 2010 here, clearly you can see this says calculator allowed. Let's go ahead and read the problem and then we'll get this set up. Particle is moving along a curve so that its position at time t is x of t comma y of t, where x of t is t squared minus 4t plus 8, and y of t is not explicitly given. Both x and y are measured in meters and t is in seconds. It is known that dy dt is equal to t times e to the t minus 3 minus 1. So a couple things. Position. This will be x of t is the horizontal position with respect to time. So x of t is a quadratic representing the change in horizontal position with respect to time. Y of t is the vertical position with respect to time. We don't know y of t, but you never know. We might have to do some work with it. So since I have dy dt, which is the change in the y position with respect to time, I'm actually going to find dx dt. Okay, and dx dt will be 2t minus 4. Now what I'm going to do is in my calculator, I'm going to go into function mode, and I'm not going to use parametric mode. I'm just going to go strictly into function mode, and I'll show you why in a little bit. But in y1, I'm actually going to put dx dt. And in y2, I'm going to put dy dt. Okay, so go ahead, take your calculator out. Make sure you're in function mode. In y1, put dx dt, which is 2t, minus 4. Now you'll actually, since you're in function mode, you'll have to enter that in as 2x minus 4, but that's okay. And in y2, you're going to put t times e to the t minus 3 minus 1 with an x instead of a t. So e to the x minus 3 minus 1. Okay, those are inputted for y1 and y2. In y3, just in case, I'm going to put x of t. Just in case I need to use it for a quick reference, so I'm going to put in x squared minus 4x plus 8. Okay, so I've got all those available to me if I need it. So let's look at part A. Part A says find the speed of the particle. Well, the speed of the particle, using a form of the distance formula, will be the square root of dx dt at t equals 3 squared. So for me, what that's going to look like is y1 of 3 squared plus dy dt located at 3. So that'll be y2 of 3 quantity squared. Using my calculator, the square root of that comes out to be 2.82. Don't forget to go to 3 decimal places as well as to use units of measure, meters per second. Okay, part B. Part B says find the total distance traveled. Total distance from 0 to 4, or t equals 0 to t equals 4. Take the absolute value of the square root of dx dt squared plus dy dt squared. So that'll be y1 squared plus y2 squared. Now in our calculator, we'll have, with respect to x, seeing that we're in function mode. So the total distance traveled ends up being 11.587 meters. That's rounded to 3 decimals as requested by College Board. Okay, part C. Part C says for the time, or find the time between 0 and 4 when the line tangent to the path of the particle is horizontal. So a tangent line is horizontal when the following is true. dy dt is equal to 0, and dx dt is not equal to 0. If both are equal to 0, then we have a situation where the particle is at rest. Therefore, I want my horizontal change to be something other than 0. I want my vertical change to be 0, so that tangent line is horizontal. Okay, so as I graph these, okay, I did a quick graph of this, and it looks like the following. Let me sketch it here real quick. Okay, dx dt looks something like this, right? Which makes sense. Dx dt was 2t minus 4. dy dt looked kind of like this, which was, I'm just going to actually write it as dy dt. Okay, I don't want to write that all the way out. All right, so now what did I do? I found where dy dt equals 0. And dy dt equals 0. Okay, so I could write this as y prime of 2.207. I found that that value is 2.207 equaled 0. Okay, so this t value was 2.207. So as I look at this, the same output on dx dt is positive. So x prime, oops, I guess I'm switching to blue, at 2.207 was greater than 0. Okay, so that works for me. This is the time at which the tangent line is horizontal. So the tangent line is horizontal at t equals 2.207 seconds. Okay, the question continues on and says, is the direction of the motion of the particle toward the left or toward the right at that time? Give reasoning. I would say it is to the right. Particle is moving right. At this time, t equals 2.207, and that's because x prime at that value, 2.207, is greater than 0. Okay, outstanding. Now I want to explain something at this point. I chose to use function mode here because when I'm in function mode, I can see each of these graphs independently. Okay, if I'm in parametric mode, all I see is the path of the particle. So I can't see the change in x and the change in y as easily. Okay, and something's bothering me here. I'm going to put a little arrow on the end of dy dt there. And actually, while I'm at it, okay, never mind. I can't erase that blue marker there for dx dt. But clearly, it'd be nice to be able to see both components change horizontally in position, change vertically in position at the same time. Okay, let's look at part D. It says there is a point with an x-coordinate of 5, which the particle passes through twice. Find each of the following. Okay, so it says the two values of t when the x-coordinate is 5. So what I want to know is where x of t equals 5. Okay, so that's relatively easy to work with. What I could do is a couple things. Since I've stored x of t as y3, I could just look at my graph and find out where y3 equals 5. Or I could algebraically work with this and say, well, t squared minus 4t plus 8 equals 5, and use my ability to factor, or maybe use the quadratic formula depending on what I need to do. In this case, I would use my calculator, and the calculator yields for me values of t equals 1 and t equals 3. Okay, so in this case, I've got my values now for part 1. I'm going to squeeze that in there. There we go. Part 2. Let's find the slopes of the lines tangent to the particle's path at each of those points. Okay, so what I need to do here is I need to find dy dx. Okay, and dy dx, as we know, is dy dt over dx dt. So I'm going to find dy dx when t equals 1. And then I'm going to find dy dx when t equals 3. Now I'm going to use my understanding of dy dt and dx dt at each of these times. And so dx dt was y1. Okay, so dx dt will be y1 at 1 and y1 at 3. Okay, and dy dt was y2, so I'll do y2 at 1 and y2 at 3. Okay, recall that this will be dy dt at t equals 1. This will be dy dt at t equals 3, and the same thing for dx dt in the denominator. So the slope of the tangent line to the particle's path at that point, or those points, the first would yield a slope of 0.432, of course using our calculator, and the second would yield a slope of 1. Okay, part 3. It's going to get kind of interesting here in part 3. Find the y-coordinate of that point, given that y of 2 is equal to 3 plus 1 over e. Okay, now we don't explicitly know y of t, so we've got to use the fact that we can integrate in order to find y of 3. So the integral from 2 to 3 of dy dt, which is y2, integrated with respect to x. Okay. Now I could write this as the integral from 2 to 3 of dy dt with respect to t will equal y of 3 minus y of 2. Right? Same thing would be true over here. This would be y of 3 minus y of 2. Okay, so using my calculator, regardless of what mode I'm working in, I can calculate this value, right? Which they should be the same. Okay, so when I calculate that using my calculator, I get 0.632120,558. Okay, likewise over here, I'm just not going to do the work over there. I don't know y of 3, but I do know y of 2. Y of 2 is this 3 plus 1 over e. So all I'm going to do is I'm going to solve for y of 3 by adding 3 plus 1 over e to that value 0.632120,558. And it comes out to be 4. So the y position at time 3 is 4. All right, guys, there you have That's a FRQ 2010 style using some parametric curve work. All right, let's look at 2006. All right, here we are, 2006. Example number 10 from the BC exam, Form B, calculator clearly allowed. I've got dx dt and I've got dy dt. It says an object moving along a curve in the xy plane is at the position x of t, y of t at time t, given dx dt and dy dt for t greater than or equal to 0. At time t equals 1, the object is at the position 2, negative 3. So again, in my calculator, in y1, I'm going to plug in dx dt. So that'll be the tangent of e to the negative x. Of course, in function mode, I'm required to use an x instead of a t, but same difference. Y2 will be secant of e to the negative x. And this information is pretty important. This tells me that that tells me that x of 1 is equal to 2, and y of 1 is equal to negative 3. All right, let's utilize that information. First of all, punching in those functions for y1 and y2. All right, so your functions should be in y1 and y2 for dx dt and dy dt. Let's look at part A. It says write an equation for the line tangent to the curve at the position 2, negative 3. Okay, so in order to write a tangent line equation, we need two things. We need a point, which we are given, 2, negative 3, and we need a slope, which we need to figure out. That's where a majority of the work on this problem will come. So dy dx is going to be equal to dx dt over dy dt. Dy dt over dx dt, but I want it at time t equals 1. So I'm going to take y2 of 1 over y1 of 1. Recall that this would be dy dt at t equals 1, and the denominator would be dx dt at t equals 1. This value for dy dx at t equals 1 ends up coming out to be 2.780. Okay, so now utilizing that, I can write the tangent line equation. So the tangent line equation would be y minus the y value, which is a negative 3, is equal to slope x minus the x value. There you go. That's part A, tangent line equation, which is tangent to the curve at the point 2, negative 3. Okay, part B. Part B says find the acceleration vector and the speed of the object at time t equals 1. Okay, so the position vector, okay, x of t, y of t, that's the position vector. The velocity vector will be x prime of t, y prime of t. The acceleration vector would be x double prime of t, y double prime of t. Okay, now I could use the notation, right? X of t, y of t, and then dx dt, dy dt. And then for the acceleration vector, I could use d2x dt squared, d2y dt squared. That would be the acceleration vector. Now, if I want the acceleration vector at time 1, I'm just going to take and manipulate this to be dx dt, d squared x dt squared at t equals 1, comma d squared y dt squared at time 1. That'll be my vector. Okay, that can be done in a number of different ways. Okay, but using our calculator, we could take the derivative of y1 at time 1 and the derivative of y2 at time 1. That's how we would get our acceleration vector. So the acceleration at time 1, using that method, ends up coming out to be negative 0.423, comma, negative 0.152. There's your acceleration vector at time 1. Looks like the acceleration is negative in both the x and the y direction. Let's just check out speed. Speed should be a quick calculation after that. Speed will be the square root of dx dt evaluated at 1 squared. So that would be y1 at 1 squared plus y2 at 1 squared. That speed comes out to be 1.138. And it looks like, do we have units? We do not have units, so I would just leave it like that. Okay, part C. Find the total distance traveled from time t equals 1 to time t equals 2. So total distance will be, as we've seen before, from 1 to 2, absolute value, y1 squared plus y2 squared, square root of that, absolute value with respect to x in this case, clearly because I'm in function mode. Okay, so of course, reminder that y1 and y2 represent dx dt and dy dt. Okay, so the total distance traveled comes out to be 1.059 units. Okay, so just so you know, total distance traveled on a parametric function. All right, let's say the parametric looks like this. All right, and let's say time t equals 1 is located here. So this point is t equals 1, and then, or excuse me, I don't know what the x and y values would be. This would be x of 1 and y of 1. Okay, and then let's say that this point right here is the point, the position at time 2, and the y position at time 2, whatever that might be. Well, this calculation for the total distance would be the length of the curve. Okay, so that would be the length of the curve on that interval. It's pretty cool stuff. Okay, let's look at part D. Part D says, is there a time when t is greater than or equal to 0, which the object is on the y-axis? So on the y-axis, what does that mean? Well, on the y-axis implies that at some point x of t is equal to 0. All right, so let's determine whether or not x of t ever equals 0. Well, if we looked at dx dt, okay, dx dt, which we represented as y1, is always positive, right? Is positive when t is greater than or equal to 0. So with that being said, if we can show that the initial position, let's show that x of 0 is greater than 0, then we will know that the particle never makes contact with the y-axis. Okay, now this may not be true, but if we can show, let's do this. If we can show that x of 0 is greater than 0, then the particle starts to the right of the y-axis and continues on, right? Okay, so let's see how we could do that. So we could find x of 0, right, by taking the integral from 0 to 1 of dx dt. Dx dt is y1. What that would give us is, well, I guess in this notation, it would be x of 1 minus x of 0. Right, so the integral from 0 to 1, when we calculate that, comes out to be 0.776. Okay, so the distance traveled by the particle in the x direction for those first 1 units of time, okay, is 0.776 units. Well, I don't know x of 0, but I do know x of 1. X of 1, based on what I know earlier, is that x of 1 was 2, right, given earlier in the problem. So I can find x of 0. So if I subtract 2 from both sides, running out of space here, then I get negative 1.224 is equal to the opposite of the initial position of the x value. Therefore, x of 0, or the initial x value, is to the right of the y-axis. Thus, I'm going to just write a therefore statement. This might be going a little above and beyond, but since dx dt is greater than 0 for t greater than or equal to 0, and x of 0 is equal to 1.224, then the particle, I spelled that wrong, let's sneak an I in there, the particle never crosses the y-axis. There you have it, guys. 06. Hope that went well. Let me know if you got questions. See you in the next video.